I want to start today by putting a very specific, very painful image in your head.
Uh-oh.
I want you to visualize the end of the month. You're sitting at your desk. Maybe you've got a coffee that's gone cold. You open your email, and there it is.
The AWS bill.
The AWS bill.
The moment of truth. Or, the moment of panic, depending on how the month went.
Exactly. And usually you scan it, you wince a little, you forward it to finance, and you hope nobody asks too many questions.
The classic, look away and hope for the best strategy.
But today, I want to look at one specific line item. Let's say you are running a standard batch workload. Data processing, video rendering, scientific modeling.
Something heavy.
Something heavy. You have 100 MBVaud X large instances, and you're running them hard 12 hours a day, every single day of the month.
Okay, that's a pretty standard heavy-duty workload for a, let's say, mid-sized tech company. You're churning through a lot of data.
And if you are doing this the safe way, the traditional way, using on-demand instances where you pay the full sticker price,
Right.
that single line item comes out to $6,912.
Which, honestly, for a company of any size, is just kind of accepted. It's the cost of doing business.
Yeah.
Nearly $7,000 for compute.
Right. But now I want you to imagine looking at that same bill for the exact same amount of work, same performance, same duration, same hardware.
Okay.
But the number isn't $7,000. It is $2,088.
That is a significant delta.
Yep.
You're looking at, what, less than a third of the cost?
It's nearly a $5,000 difference per month.
Wow.
Over a year, that is $57,888 just sitting there on the table.
$57,000.
That is a 70% reduction in cost.
When you put it in annual terms, that's the salary of a junior engineer.
Right.
Or a very, very nice team offsite in Hawaii.
Exactly. And if I told you I could save you $50,000 with one switch, you'd probably tell me I'm selling snake oil.
I would absolutely assume it's a scam, 100%. Or that there's a massive hidden fee like, oh, by the way, we own your IP now.
And you'd be half right. It's not a scam. It is the reality of the AWS spot market. But there isn't a hidden fee. There is a hidden threat.
The catch. There's always a catch.
The catch is volatility. The catch is that at any moment, without asking for your permission, Amazon can tap you on the shoulder and say, I need that computer back. You have exactly 120 seconds to pack your bags and get out.
The infamous 2-minute warning.
And if you aren't ready for it, if your architecture isn't built to handle that eviction.
It's carnage. It's absolute carnage.
Yeah.
Processes die midstream. Data gets corrupted. Network connections are just severed. It is absolute chaos.
And that fear of the 2-minute warning is why so many engineering teams look at that $50,000 in savings, shake their heads, and stick with on-demand.
Yeah, they choose safety over savings because keeping the lights on just feels more important than optimizing the bill.
But today, on this deep dive, we are going to challenge that binary. We are going to bridge that gap. We are talking about the tool that acts as the negotiator between that chaos and your application.
Right.
We're talking about Karpenter.
Karpenter is fascinating because it fundamentally changes the relationship between Kubernetes and the cloud provider.
How so?
It stops treating the cloud like a static data center you just rent space in. It starts treating it like a dynamic, real-time market.
Okay, so based on the documentation we have, Karpenter is defined as an open-source node lifecycle management project.
Right.
Which is, it's accurate, but it's also incredibly dry.
It's very dry.
Yeah.
It sounds like something you install, check a box, and just forget about. It doesn't capture the power at all.
But our mission today is to prove it's much more than that. We want to explain how to combine Karpenter's automation with AWS Spot instances to get those massive savings without crashing your application. We want to move you from just hoping the server stays up, to understanding the economics and the mechanics of a truly fault-tolerant architecture.
And I think the key mindset shift here, and we'll come back to this a lot, is realizing that savings require architecture.
Savings require architecture. I like that.
You cannot just toggle a switch to Spot and hope for the best. You have to build a system that expects to die.
Expects to die. That is ominous. I love it. So before we get to the death and destruction, let's unpack the mechanism.
Yeah.
Let's talk about Karpenter itself.
Sure.
To really appreciate Karpenter, I feel like we have to bash the old way of doing things a little bit.
Absolutely.
In the old days, which in cloud years is like, what, 2020?
Yeah, basically.
We relied heavily on the cluster autoscaler.
Right. The cluster autoscale, it was fine. It did the job, but it was reactive in a fairly dumb way.
How so?
It worked with auto-scaling groups, or ASGs, so you have to predefine these groups. Here is my group of M5.large nodes. Here's my group of T3.medium nodes.
It felt like you were manually organizing inventory shelves before the customers even arrived. You had to guess what people would buy.
That's a perfect analogy.
Yeah.
And if a pod came along that needed, say, a GPU, but you hadn't set up a GPU auto-scaling group.
Too bad.
Too bad. The pod just sat there pending. The cluster autoscaler would look at the ASGs and say, well, I can add more of what we have, but I can't make something new for you.
Karpenter takes a completely different approach. It just bypasses those groups entirely.
It does. It talks directly to the cloud provider API. It's what we call groupless autoscaling. But the real magic is in its core loop.
Okay.
According to the documentation, this loop has 4 distinct phases: watching, evaluating, provisioning, and disrupting.
I want to break these down because this loop is essentially the heartbeat of a modern cluster. Let's start with phase 1, watching. What is it watching? The stock market.
Not quite, though it does act like a trader sometimes. It's watching the Kubernetes scheduler.
Okay.
So to understand this, you have to understand the drama of a pod's life. A pod is created. It says, I exist. Put me somewhere. The Kubernetes scheduler looks at the available nodes, the in, so to speak.
And if the in is full?
The scheduler marks the pod as unschedulable. It effectively says, sorry, no room. That status change, that flag going up, is the bat signal for Karpenter.
Ah.
It sees that pending state, and it springs into action.
Okay, so Karpenter sees the signal. We have a homeless pod. Now we move to phase 2, evaluating. This isn't just buy any server, right? It's not just throwing warm bodies at the problem.
Oh, not at all. And this is where Karpenter is significantly smarter than the old tools. It acts like a bespoke tailor or a personal shopper.
I like that.
It looks at the pod that is stuck. It reads the manifest line by line. How much CPU does it need? How much memory? Does it require a GPU?
What are the zones?
Exactly. Does it need to run in a specific availability zone? Does it need to run on a specific operating system? It reads everything.
So if my pod says, I need high-frequency compute, I need to be in US West 2A, and I refuse to run on anything older than 2022 hardware, Karpenter reads all of that.
Precisely. It builds a shopping list based on the exact specific constraints of the pending work. It resolves all those requirements into a concrete set of hardware options. It's not guessing, it's calculating.
Which leads right into phase 3, provisioning, the shopping trip.
Karpenter takes that list, calls the AWS API, assuming you run AWS, and says, I need a node that meets these exact specs, and I want it now.
And because it's talking directly to EC2, to the Crate Fleet API, it's incredibly fast.
Super fast. The documentation mentions it's often up and running in under a minute.
It really is like a just-in-time manufacturing system. You don't hold inventory. You order parts the second the assembly line signals a need.
Right, which cuts out so much waste because you aren't paying for empty capacity just in case.
And finally, phase 4, disrupting. This sounds negative. Why are we disrupting things? Usually we want stability.
In this context, disruption is a positive force. It's about efficiency and consolidation.
Oh, yeah.
Imagine you have a large server, an X large, and it's only running one tiny pod because everything else finished its job and went home.
You're paying for a mansion to house a hamster.
Exactly. Bad economics.
Terrible economics.
So Karpenter notices this. It monitors the utilization of every node. It says, hey, I can move that hamster to a smaller house. It provisions a smaller, cheaper node, moves the pod, and then terminates the expensive empty one.
No, cleans up after itself.
It cleans up the mess so you aren't paying for empty warehouses. It effectively defrags your cluster automatically.
So that's the mechanism. Watch, evaluate, provision, disrupt. It sounds great on paper, but for this to work effectively, especially when we introduce the chaos of Spot instances, we need to give Karpenter some rules of engagement. We can't just give it the corporate credit card and say, go wild.
Correct. And in the documentation, this configuration layer is called the NodePool.
The NodePool. This is a custom resource definition, a CRD. So it's basically a YAML file where we define the boundaries.
Exactly. Think of the NodePool as the corporate spending policy. It tells Karpenter what it is allowed to buy. You can buy sedans, but not Ferraris.
There are a few key concepts inside this NodePool that I found really interesting. The first one is taints. Now, taint is a terrible name for a feature, by the way.
It's classic Kubernetes naming. They love their slightly gross metaphors.
They really do.
But the concept is crucial for safety. A taint is like putting a do not enter sign on a server. Or better yet, think of it like a biohazard sign.
Okay.
You taint a node so that normal pods don't accidentally wander onto it.
Why would I want to do that in the context of Spot instances?
Imagine you have a critical database
Hmm.
or the dashboard that the CEO looks at every morning.
Right, something that cannot go down.
That workload absolutely cannot handle being shut down randomly. You do not want Karpenter to accidentally place that database on a temporary volatile Spot node just because they had some free CPU.
So you take the Spot nodes, you say this node is volatile.
Exactly. And only pods that have a special pass, called a toleration, can land there. It's like a VIP section, but the VIP section is actually a war zone. Only the soldiers are allowed in. The civilians, like your database, stay out.
I like that. The war zone taint. Okay, what about requirements?
This is really the meat of the configuration. Requirements are the filters. This is where you tell Karpenter, you are allowed to buy M5 and C5 instances, but stay away from T3 burstable instances because they're too slow.
Or you can use us West 2A, but stay out of us East 1.
Exactly. And most importantly for our deep dive today, this is where you set the capacity type.
Right, capacity type Spot on demand. This is the toggle that unlocks the savings.
That's the one.
And finally, limits.
The safety valve. This is critical. You could set a total CPU or memory limit for the cluster.
And that stops what? A runaway process?
It stops Karpenter from infinitely provisioning nodes if your code has a bug and starts requesting 1 million pods in an infinite loop. It prevents you from waking up to a bankruptcy-level cloud bill because of a recursive loop in your code.
So the NodePool is what the infrastructure team sets up. It's the rules of the road. But then there's the other side of the coin, the pod spec. This is what the developer writes.
Right, and the connection between the two is vital. The NodePool is the supply, the pod spec is the demand.
So how does the workload ask for specific hardware?
Well, the simple way is with a node selector or node affinity. If a developer knows their app needs high-frequency processors for video encoding, they can put a selector in the pod spec asking for a specific instance family.
Okay.
But there is a more advanced concept here called topology spread constraints.
That is a mouthful. What does it actually do?
It's a fancy way of saying don't put all your eggs in one basket.
Oh, okay.
If you have, say, 10 copies of your application running for high availability, and Karpenter puts all 10 of them on the same physical node to save money,
And that one node gets the 2-minute warning?
you lose everything. Your entire service goes dark instantly. Topology spread constraints. Tell the scheduler, please spread these pods across different availability zones, or at least across different physical hosts. It maximizes your survival rate. It forces Karpenter to buy diverse infrastructure.
Okay, so we have the engine Karpenter, we have the rules node pools. Now we need to talk about the fuel, the cheap, volatile fuel that makes this whole thing worth it.
The spot market.
The spot market.
Let's get into the economics, because a lot of people think Spot is just cheap servers. But why are they cheap? It's not because they are broken or old.
Right. The source material puts it really simply. AWS has massive data centers. They have to build enough capacity for the busiest day of the year. Cyber Monday, Prime Day, the Super Bowl.
Exactly. To handle that peak, they have to build just massive amounts of excess capacity. But on a random Tuesday in March, or at 3 a.m. on a Sunday,
That capacity is just sitting there.
empty, consuming power, consuming cooling, depreciating. It's a wasting asset.
So they sell it at a discount.
A massive discount,
Right.
up to 90%. That is what a Spot instance is. It is the unsold inventory of the cloud.
It's the empty seat on the airplane 5 minutes before the doors close.
That's the perfect analogy.
The airline would rather sell it for $10 than fly it empty.
Exactly.
Hmm.
But unlike an airline seat, they can kick you out of this seat mid-flight if a full-price customer shows up.
That's the key. If a customer walks up with a full fare ticket, AWS looks at the Spot users and says, sorry, you gotta go. Now, there's a nuance here that I think is critical. It's not just one big bucket of Spot instances, right? It's not like there is a single Spot store.
No, and understanding this is the secret to stability. It really is. AWS groups capacity into pools.
Cool.
And a pool is defined by the combination of instance type and D-availability zone.
Can you give me a concrete example of that?
Sure. M5.xlarge in SWest2A is one pool.
Okay.
And M5.xlarge in USWest2B, just a few miles away, is a completely different pool.
Even though it's the same hardware.
Same hardware. And a C5.xlarge in that original SWest2A zone is a third distinct pool.
Why does that distinction matter so much to the listener?
Because supply and demand are local to the pool. An interruption in one pool does not affect the others.
Ah, so it's not a global event.
Not at all. If everyone in the world suddenly wants M5.xlarge instances in USWest2A, Maybe there is a conference happening in that zone, or a big company is doing a rollout. AWS might reclaim all of those specific machines.
But the C5 instances next door...
They might be completely untouched. The M5 is in a different zone. Untouched.
Yeah.
It's like traffic. Just because Main Street is gridlocked doesn't mean the highway is clear.
So the volatility is localized. It's compartmentalized.
Exactly. It's patchy. And Karpenter is smart enough to navigate that patchiness if we let it.
But when that volatility hits your pool, that's when the trouble starts. That's when the landlord comes knocking.
The reclaim.
Let's walk through this. AWS gets a full-price customer. They need the computer back. They issue the reclamation notice. We are back to the 2-minute warning.
T-minus 2 minutes. The clock is ticking.
I want to slow this down. I want to walk through the architecture of an interruption. Because Karpenter doesn't just magically know a node is dying, right? It needs a tap on the shoulder.
Correct. And this is a critical setup step a lot of people miss. If you don't set this up, Karpenter is flying blind.
Okay.
The source material outlines a specific flow here. It starts with the AWS EC2 Spot service issuing an event.
And that event goes where? A webhook.
It goes to EventBridge, which is AWS's main event bus. From there, it is routed to an SQS queue-simple queue service. This queue is usually named something like Karpenter Interruption Queue.
Why SQS? Why not just a direct API call or something?
Reliability. 100% reliability. If Karpenter is restarting or upgrading or the network just blips for a second, a webhook might fail. The message gets lost.
And if you lose that message...
You lose your 2-minute warning, you're done. SQS holds the message until Karpenter is ready to read it. It guarantees delivery. It's the answering machine that makes sure you get the message.
Okay, so Karpenter is watching that queue relentlessly.
Constantly pulling it. Any bad news, anything for me.
So let's visualize the timeline. This is the 2-minute drill. Put us in the server room. The clock starts at T-minus 2.00.
Okay, T-minus 2.0. AWS sends the instance action notification. It hits EventBridge, then lands in the SQS queue. The clock is officially running.
T-minus 1.55, 5 seconds later.
Karpenter's next poll hits the queue. It picks up the message. It reads the instance ID and matches it to a Kubernetes node in your cluster. It knows, okay, node A is going down.
T-minus 1.54, 1 second later. What does Karpenter do first?
Cordoning. It immediately marks that node as unschedulable. It's triage. It stops the bleeding. It ensures no new work gets sent to the dying server. You don't want to start a new job on a sinking ship.
Smart. So the bridge is closed, T-minus 1.53.
Draining. This is the active phase. Karpenter starts evicting pods. It goes to the pods currently running on that node and says, you need to leave right now.
Now, does it just kick them all off instantly? Is it a hard kill?
It tries to be polite first. It respects pod disruption budgets, or PDBs. We'll talk about those later. But basically, it checks if it's allowed to kick them off without breaking the application's own rules.
Okay, so assuming it is allowed.
T-minus 1.50. The pods get the message.
And what does that message look like to a pod?
Graceful shutdown. The pods receive a SIG term signal. This is the polite knock on the door from the operating system. Ideally, this is where your application starts packing its bags.
Checkpointing data, closing database connections, flushing buffers to disk.
All that good cleanup stuff.
Okay, T-minus 1.20. We're 40 seconds into the crisis.
Rescheduling. The pods have shut down or been forced down if they ignored the signal. They enter a pending state in Kubernetes. They are now officially homeless, looking for a new home.
And Karpenter sees this.
Karpenter sees this new pending work and, if needed, starts buying a new node to replace the dying one immediately.
So the recovery actually begins before the death is final?
Ideally, yes. If your shutdown is fast enough, you can be back up and running on a new node before the old one even disappears from the console.
And then T0?
Termination.
Yeah.
AWS pulls the plug. The hardware is gone. If your app was still trying to save a file, too bad. If a database transaction was half open, it's severed.
That is intense. 2 minutes is not a lot of time.
It feels like a lifetime for a computer. But if your application is sloppy or if it hangs while shutting down, 2 minutes goes by in a blink.
So knowing that this drill is going to happen probably often if we want those sweet, sweet savings, how do we configure Karpenter to survive it? Let's talk strategy.
The first and most effective strategy is diversification.
This is the senior engineer insight, right?
100%. Don't just pick one instance type. If you set your NodePool to only allow M5.x large, you are betting everything on one horse. And that horse might get sick.
We talked about the math of pools earlier.
Yes. Let's look at the numbers again. If you allow one instance family in 3 zones, you have 3 pools. That is high risk. If one pool has a shortage, you lose 33% of your capacity options instantly.
But if we expand that list...
Say we allow M5, M6i, C5, C6i, R5, and R6i. That's 6 families. times 3 zones. That is 18 pools. The odds are much better.
And if we go maximum diversification,
The source mentions a spot fleet approach, where you allow maybe 13 families in 3 different sizes, large, X large, 2X large. That gets you to 117 pools.
and the probability of all 117 pools being sold out at the exact same moment.
Is near 0. Unless the entire AWS region goes offline, in which case we have much bigger problems than spot pricing, there will be capacity somewhere.
And Karpenter will find it.
Karpenter will find the cheapest available option in that massive menu.
So broaden your horizons. Don't be picky about hardware.
Exactly. For most batch processing, CPU is CPU. Memory is memory. Don't get attached to a specific model number. Treat compute like a commodity.
Okay, strategy 2. Taints and tolerations. We touched on this, but let's formalize the strategy.
This is about protecting the innocent. You apply a no-schedule taint to your spot nodes in the node pool. It effectively says, danger, high voltage, volatile area.
And only the qualified electricians get to touch it.
Right. Your batch jobs, the ones you've engineered to handle interruptions, get a toleration added to their pod configuration. They are allowed to land there.
But your legacy database, your fragile admin console,
They don't have the toleration, so Karpenter is forced to place them on stable on-demand nodes. It physically can't schedule them in the danger zone.
it effectively creates 2 zones in your cluster, the safe zone and the danger zone.
Exactly, and you choose which zone your app lives in based on its resilience.
Strategy 3 is interesting because it deals with what happens when the spot market completely dries up. Fallback to on-demand.
This is your insurance policy. This is critical. You configure your node pool requirements to accept both spot and on-demand. Now, there is a myth here I want you to bust. I've heard people say, if I list spot first in the list, Karpenter tries spot first. Is that right?
Yeah, that's a common misconception. People see that array in the YAML values, spot, on-demand, and they think it acts like a priority queue.
That it tries the first one, and if it fails, tries the second.
Right. It doesn't work that way. Karpenter doesn't read top to bottom like a human.
So how does it decide?
Karpenter uses a strategy called price capacity optimized. It looks at the whole picture. It looks at the real-time price, sure, but it also looks at the depth of the capacity pools. It asks, which pool is least likely to interrupt me in the near future?
So it's smart enough to know that a super cheap pool with a high interruption risk might actually be a bad buy.
Exactly.
Yeah.
And in practice, it almost always chooses Spot because it is cheaper and usually widely available. But if Spot is gone, if Black Friday hits and there are 0 Spot instances available in your entire region,
It seamlessly switches to on-demand.
it doesn't fail. It doesn't give up. It just pays full price for a while to keep your business running. That seems like the best of both worlds. You save money when you can, but you prioritize uptime when you have to.
It is. It's the responsible senior engineer way to configure it. It prioritizes availability over pure cost, but it takes the cost savings whenever they're safe to take.
So we have the infrastructure set up, we have Karpenter watching the queue, we have diversified our pools, but, and here is where it gets really interesting, none of this matters if the code running on the server is garbage.
That is the hard truth. You cannot fix bad code with good infrastructure. You can build the most sophisticated Karpenter setup in the world, but if your app just dies the second it gets a restart signal, you're going to have a bad time.
Making a workload spot ready is a development task, not just an ops task.
100%.
The source material lists 3 pillars of spot readiness. Let's go through them. Pillar 1, checkpointing.
This is absolutely crucial for long-running jobs. Imagine you are processing a massive video file rendering a 4K movie, and it takes 4 hours.
Okay.
If the node dies at 3 hours and 59 minutes, what happens?
If you aren't checkpointing, you start over from 0. You just wasted 4 hours of compute and time.
Exactly. And you paid for those 4 hours of electricity for nothing. Checkpointing means saving your progress regularly. Maybe every 60 seconds or every 100 frames of video, you write the current state to S3 or a database.
So if the node dies,
The new pod spins up on a new node, it reads the last checkpoint, and it resumes from the 3-hour, 59-minute mark.
so you only lose that last minute of work, not the whole 4 hours.
Right. It turns a catastrophe into a minor hiccup. And this changes the economics, too. If you have to restart constantly, Spot might actually be more expensive than on-demand because of all the wasted work. Checkpointing is what preserves the savings.
Pillar 2, graceful termination. We talked about the sig term signal.
You have to handle it. You have to write code that handles it. By default, many applications, especially older ones, just ignore signals. They just keep chugging along until the operating system kills them with a sig kill.
You have to catch it.
You need to write code that specifically catches that sig term.
And what should that code do, ideally?
It should stop accepting new requests immediately. It should finish what it is currently doing, it should save its state, and then it should disconnect cleanly from its dependencies.
It's like closing down a restaurant.
Exactly. You lock the front door so no new customers come in, but you let the people already eating finish their meal.
There is also a Kubernetes setting here that trips people up. Termination grace period seconds.
Yes, this is a big one. This is how much time Kubernetes gives your pod to clean up before it gets impatient and uses sig kill, which is the die now signal, the SWAT team kicking down the door.
What's the default?
Usually 30 seconds, which is often not enough.
Is 30 seconds enough to finish a big database transaction or upload a large file to S3?
Often, no. You need to set this high enough to finish your cleanup, say, 90 or 100 seconds.
But it has to be less than the 2-minute hard limit from AWS, right?
Absolutely. You cannot negotiate with AWS. If you set your grace period to 5 minutes, it doesn't matter. AWS pulls the plug at 2 minutes, regardless of what your config says.
Right.
You cannot negotiate with the laws of physics or the AWS terms of service.
Pillar 3, statelessness.
This is Cloud 101, but it bears repeating, especially here. Do not store important data on the local disk of the node.
But it's faster, says the developer.
It is faster, for a little while, until the node vanishes and takes your data with it into the digital void.
If the node is ephemeral, the local disk is ephemeral.
Exactly.
So where does the data go?
S3, EFS, DynamoDB, an external database. Anywhere but the local disk. The node should be disposable, the data should be persistent. If you follow this rule, losing a node is a non-event. If you break this rule, losing a node is a resume-generating event.
I want to touch on one more configuration piece that is dangerous. Pod disruption budgets, or PDBs.
PDBs are tricky. They're rules that you give to Kubernetes that say you must keep at least this many copies of my app running at all times.
So something like min available.
Right. That means Karpenter. You can drain nodes, but make sure one of me is always up. And that's generally a good thing. It prevents Karpenter from evicting all your replicas at the exact same second, which would cause an outage.
But there is a trap here.
A huge trap. If you set your PDB too strictly like min available, 100% for a workload with only one replica, you have effectively handcuffed Karpenter.
Because it can't evict anything. It would violate the budget.
Right. Karpenter tries to drain the node. The PDB says, no, I need 100% uptime. And Karpenter just waits and waits.
And then T0 hits.
And then T0 hits, AWS kills the node, and you have a hard crash anyway. You fought the law and the law won.
So you need to leave room for disruption.
PDB should be realistic.
Sure.
Allow for some turbulence. If you have 10 replicas, set min available to 8 or 9. Give the system room to breathe and maneuver.
Let's move into the advanced patterns. We have the basics down. How do power users do this?
One pattern I really love is the baseline plus burst.
Okay, how does that work?
You run a steady baseline of on-demand instances, say enough to handle your minimum traffic, your 3 a.m. traffic. This guarantees stability for your core operations.
So you know the site will never go completely down.
Right, you have that rock-solid foundation.
And then for the spikes, the daytime traffic, the product launch.
You let Spot instances handle the burst. You configure it so that any traffic above that baseline spills over onto cheaper but volatile Spot nodes.
So if Spot disappears, your users might experience slowness because you lost the burst capacity, but the site stays up because the baseline is solid.
Exactly. It's a fantastic risk mitigation strategy. You used taints like baseline versus burst to control where the pods land. It's perfect for e-commerce sites dealing with holiday traffic.
Another pattern is the time-based strategy.
This just leverages the supply and demand curve we talked about earlier. Nighttime is cheap. Weekends are cheap.
So you run your heavy data processing at 3 a.m. on Spot.
And during the day, when prices might spike and interruption risk is higher, you might switch your configuration to favor on-demand. You can actually automate the NodePool configuration to change based on the time of day.
Now let's talk about the gotchas, the pitfalls. Where do smart people go wrong with this?
The biggest one, by far, is missing the queue.
The SQSQ again?
It's the Achilles heel. People install Karpenter, they set up the node pools, they high-five each other, but they forget to configure the event bridge rule to send events to SQS. Or they configure it in the wrong region.
So what happens?
Karpenter never gets the T-2 minute warning. It thinks everything is fine, the whole system is just blissfully unaware.
Until the server just disappears from under it.
It's the silent death. You lose the graceful shutdown window entirely. You go from running to dead instantly. If you had in-flight work, you have a 100% data loss risk.
It negates all the work you did on graceful termination code.
Exactly, because the code never gets the signal to run.
Ouch. What else?
Zero grace period. Developers leaving termination grace period seconds at the default, or worse, setting it to 0 because they want fast deployments.
They want the pod to die fast so the new one comes up fast.
Right. It makes their CI/CD pipeline look faster. But if you set it to 0, when the spot interruption signal comes, the pod dies instantly.
And drops whatever transaction it was holding.
It's self-sabotage. You are prioritizing deployment speed over data integrity, which is almost always the wrong trade-off.
And the third one?
Stateful workloads on Spot. Just trying to run a standard Postgres or MySQL database on Spot.
Just don't do it. Is that the advice?
Just don't. Unless you have an incredibly sophisticated replication strategy, like a multi-master setup that can handle random node loss without any data corruption, it is a recipe for disaster.
So what do you do?
Use Node Affinity. Force those databases onto on-demand nodes. It's worth the extra money for the sleep you'll get. Don't gamble with your persistent data.
How do we know if we are winning? What metrics should we be watching to know if our spot strategy is healthy?
You definitely want to look at OSSEC to spot interruption total in your monitoring. How often are we getting hit? If it's every 5 minutes, maybe your instance types are too popular, or you're in a very constrained zone.
You might need to change pools. Add more instance families to your list?
Right. If you're constantly getting interrupted, you're losing efficiency from all the restarting. And you should watch Karpenter node replacement duration seconds.
Okay, what does that tell you?
When a node dies, how fast are we recovering? Are we back up and running in 45 seconds? Or is it taking 5 minutes? That tells you if your pod startup scripts are efficient or if they're slow.
There's also a tool mentioned called the Spot Instance Advisor.
Yeah, that's an AWS tool. It's super useful. It shows you historical interruption rates. You can look up m5.xlarge in US East 1 and see, oh, this has a greater than 20% interruption rate recently. Maybe avoid that one for a while.
It's like checking the weather before you go sailing.
Exactly. It helps you pick the calmest waters.
Okay, let's unpack this all. What does this mean for the listener? We started with the promise of 70% savings.
And that savings is real. We see companies achieving that every day. But the senior insight here is that Spot isn't just a billing trick. It's not just a config switch.
No.
It's an architectural commitment.
It forces you to be better.
It forces fault tolerance to be the default state of your application. You aren't just handling failure when a server dies once a year. You're handling failure 10 times a day.
And because you are practicing it constantly.
You get really, really good at it. Your system actually becomes more resilient than a system running on stable, expensive hardware because you have exposed all the weak points. You've patched every hole in the boat because you're constantly sailing in rough waters.
That is a powerful thought. By introducing chaos, you create order.
It's the ultimate stress test. It proves your code works under pressure, not just in the lab.
So here's my final thought for you to chew on. If your application is robust enough to survive the chaos of the spot market, if it can handle random 2-minute evictions without blinking, without losing data, what else can it survive?
Anything. A bad deploy, a zone outage.
Exactly. Bad deployments, zone outages, sudden traffic spikes. If you are spot ready, you are everything ready.
It really is a proxy for code quality.
Yeah.
If you can run on Spot, you have written good, resilient, cloud-native code. Period.
So do yourself a favor. As soon as this deep dive ends, go look at your termination grace period seconds setting in your YAML files. You might be surprised at what you find.
It's probably 0, or the default 30.
It's definitely 0. And go check for that SQSQ while you're at it. Thanks for listening to the deep dive.
We'll see you next time.